已解锁，请起出话筒。
已经做了，那你做。哦，对对对，给多少钱？隐形眼镜。OK。OK. Okay. Let's start. So your assignment will be due on this Friday, right? Midnight. Okay, 11:59. If you have any question, you can ask. Yeah, about assignment. Yeah, I can give some hint if needed. Now can also. You want to ask? Questions? What me see my check? What do you mean? I mean, you have to aim for that question to be correct, right? So is it correct or not? It's not like breaking. Yeah. Huh? Mm-hmm. Axiom C. Yeah, it is what it means. If it's okay, then okay. Yeah, what? Sorry. Sorry? Let me see. Ken, you can try and give me like your argument later. See what's wrong with it. Yeah. See. Yeah. I mean, yeah. Okay. Try and give me later. Nothing is. Nothing is. Oh, your quiz. Your quiz. I put out solution, and then I forget to bring your mark quiz, or maybe I'll bring tomorrow. Then you can check your mark, and then check my marking. And then I think is okay. So maybe one agreement I want to make in between me and Chiang. So is that you can still ask your question, okay? You still can challenge me or whatever. But then if the agreement is not made in between 5 minutes, right? We should stop inside the class. We can continue outside. Okay, maybe all of you can help to do the timer. Okay, yeah, stop it. Yeah, because sometimes when we discuss, it's like a bit santo, so we will continue forever. Because it's like, for example, last week, right? The quiz one is like take me 1 hour, so I'm missing like I actually planned for 20 minutes for quiz only, so I'm missing like 30 minutes for my lecture time. So we might get delayed. Okay. But you still can ask questions, just that we don't want to dwell on the disagreement too long. Okay, because sometimes when we argue, right, we get into irrational part. So it's like we're not arguing on points anymore. We are like just want to so-called win, right? You obviously want to win, right? Once you want to challenge. So we shouldn't have that kind of mindset. So we should like listen more to each other. Okay. I try to argue with you in the Lydia style. Okay. Okay. Other than that, about listening, okay, so very important. I hope that in my class, right, you can do whatever you want. You can do whatever you want. But then I try to listen what I say. Okay, see what I say makes sense. If I not make sense, you can just ask or yeah, ask me actually. Okay, because I know that I think from tutorial or daily like conversation with you, right? I found out that your self-learning skill is very good. Okay, that one I acknowledge that. But then you need to try and learn to listen to what people say, and then try to understand what people say as well. Okay, so that your skill can try to talk to others. Understand or not? Otherwise, you just do your job on your own. You understand what I say? Okay, because I'm a different lecturer here. I'm trying to speak so that you understand. I'm not trying to speak like you don't need to understand. No. You understand what I say? Okay, so try to engage with me. Can? Okay, so but if you feel tired, you want to do your own stuff, it's okay. But then try to listen to what I say. Understand what I say. Okay? Can or not? Okay, so this is one thing. The other thing is, oh, actually, I realized now I have an advisee here, like Ping Jie and like what Chong Wei Ying, what's the name? Do you know what the advisor? Do you have your advisor? No? Oh, yeah, yeah, yeah. Advisor. You guys all have your advisor, yeah, right? So Yu Heng and actually Ping Jie is my advisor. I just found out. You guys never meet me, right? I found out an email. Right? Okay. Never mind, I will send an email again. But then now is in my class, so you don't need to see me purposely. I read this. Okay. But then if you have any problem, you should talk to your advisor. Okay, so see if you can get some advice for you. In particular, if you've like failed courses, you need to take credit, right? They have to kind of approve it. Pauline will ask you to ask your advisor first. Okay, so it's kind of important in that regard. Um, oh, one more thing about last week, right? Ping Jie thought that P implies Q is P and Q, right? So this is very important concept or idea in this world, right? So two things happen, two things are true. Does it necessarily that two things has connection on it? Does it necessarily that two things has connection on it? Sometimes it might not be, you know. It might not be. It might not be. So P implies Q and P and Q is not the same thing. But then this is a usual thing will happen in reality, you know. You understand what I say? People try to find connection, but then that connection might be false, might be just missing. You understand what I say? Like so superstitious. Can you think of like superstitious example? Can you think of some superstitious example? 有什么是 superstitious 吗？哦，for example，我早上一直看到那个号码，早知道我就去买了，出了我就去买。Yeah. Sometimes there is connection, but then sometimes you cannot prove the connection. You understand? Yes, yes, true. But then there's like very, how to say, I think you can relate this, right? In reality, like your friends or your family they will try to pull two things together that you think that might not be there's a connection. Or it's hard to prove actually, most of the time. Okay, so P implies P and not Q is not the same. Okay. Yeah. Okay. Right. Okay. Okay, good. Okay, and then if in that case, then let's start. Yeah, let's start. Let's start from recapping what we did before. Okay, last week we did a very important concept in this class. It's called supremum, least upper bound. Okay, so what's the least upper bound? So a number M R is least upper bound. There are two conditions, right? If what? Oh, then all what? In the what? Okay, so I think I left out something, right? Is the upper bound of a set X first? If what? You want to compare it. So compare what and what? That's right. That's right. So basically, you need to split this word into two parts, right? Least upper bound. Okay. So it is the upper bound, and then it is the least one. So there are two parts here. Okay. So first part, how to become an upper bound. For every element in X, it should be less than or equals to M. Okay. How to be the least one? Least among all upper bound, huh? Okay. For all other upper bound, M prime, M should be less than or equals to M. Okay. Okay. Cool. Good. Okay. There's an equivalent one, right? There's an equivalent number 2. You still remember? What's the equivalent one? What's the equivalent one? It's the contrapositive of this. If M prime strictly less than M, then that exists. No, we just straight away say that M prime is not an upper bound of X. Okay? Contrapositive. Very contrapositive. Okay. Yeah, try and practice this contrapositive. So maybe I should say that M is a upper bound here. M is upper bound implies that M is less than M prime. So here is if there exists a M prime in R such that this is true, then it's okay. Good. Is it contrapositive? Yeah, I think so. Wait, negation, contradiction. Huh? If never mind, no need there exists. Yeah. No need there exists. Yeah. Yeah, for all for all M such that this is true. For all M prime such that this is true. Okay. Does that make sense? Okay. Okay, good. So then we say that then we'll say that R is a complete ordered field. Okay, so we talk about field, we talk about ordered, and then complete is what? The completeness axiom says that every non-empty and then bounded above set has a lowest upper bound. Okay, so every bounded above set you will have a lowest upper bound. Okay, and then this one obviously have to live in R. Okay, by definition, LUB is living in R. Okay, so this is how we complete our real number. Yeah, so later, or now, should I show you like now or later? Okay, maybe now. So let's see how this completes our real numbers. So for example, proposition. So there exists a positive real number in R such that, so positive real number square root 2 in R such that square root 2 square to 2. Okay. So last time I showed you that square root 2 is irrational, right? So we started the journey to find other irrational. Okay. But then why does it exist? I didn't prove to you. Okay, so I didn't prove to you why it exists. Okay, so here this is so in mathematics you need to dissect your claim. Okay, so in this case here we want to find existence. Okay, so you need to have some, so existence either you find it for me or you get some theorem or axiom that give you existence. So it give you existence of something. Okay, so for example, completeness axiom is an existence statement. It means what? What does it mean? So if you have a non-empty bounded above set, then it will give you a least upper bound. Okay, so I don't know what is the least upper bound, but then there is one. Understand? Okay, we don't really care what is it, but it tells you that there's one. Okay, so we're gonna use this to show. So what's the proof here? So to do that, I need a set, right? I need a bounded above set, non-empty set. Okay, so I'm gonna build my set first. So let X be a set of number is real number such that X is less than 0 or X squared is less than 2. So if I'm going to use a completeness axiom, right, I need to show that it's non-empty and then bounded above. So first of all, S is non-empty. Okay, why is it non-empty? Can you find me a number that satisfies these two conditions here? Ah, 0 square less than 2, right? Yeah, 0 works. Any other number you want to try? Just now you said what, -1. Did you say -1? -1 works or not? No, no, no. Huh? So yeah, sure. Do you want to try -1? Why never mind? So in mathematics, right, there's true or false only. So you cannot get never mind one. So either it works, either it doesn't work. So you check it. -1 works or not? Works, right? Because -1 square less than 2. Yeah, sure. It's okay. Any number, other number you want to try? Or maybe try one number that's not in this set. -2 is not in this set, but -2 less than 0. Yeah. So any number that's not in this set, you want to try? Huh? 1 trillion. Okay, give other chance choice. 那边的，我听啊那边的声音，选一个号码不在这个 set 里面。Okay. So 2 is not less than 0, right? 2 square is greater than 2. Good. Yeah. So false for 2 statement. So 2 is not here. Okay, good. Okay. Yeah. So this is non-empty. So this is first part. Second part show that S is bounded above. I think this is a very similar thing that Chi Yang want to achieve last week, right? If you still remember this. Okay. So we're gonna do this now. So here's the lemma. So to do this, this is the claim. This is the claim here. So if there's a number that's greater than 0, and at the same time, Z square is, do I want strictly greater? Let me see. Okay, strictly greater or greater or equal is enough. Let me see. Can I put strictly first and then see how it goes? Okay, let me put like this first. And then Z is an upper bound for X. Or maybe I put greater or equal first. Let's put greater or equal first. Okay. Okay. Does it make sense or not? This lemma. Okay, if you compare to the set there. In the set there, everything is like either negative or the square of it is less than 2. So I pick something away from that. Okay, I pick somewhere positive and then pick something that's square root 2. Okay. Should I draw this picture? Maybe let's draw this picture of this x squared less than 2 thing. So if you still remember from last week, we can check the x squared using this parabola. So when it's equal to 2, maybe somewhere here. Okay, so everything that's less than a square that's less than 2, or anything less than 0. Okay, is it okay so far? Okay, so we want to find the upper bound that's over here. Okay, so how do you prove this? There's some technique here. So let's say proof of the lemma. So let's consider such. And then we must prove that. So this is the upper bound, right? What's the condition of upper bound? If x is in S, then S have to be less than or equals to Z. Okay. Again, upper bound definition. Okay. So we will prove by contrapositive. That is, if S is greater than Z, then we will show that S is not in S. Okay. But then what does it mean by S is not in S? Then either S is greater or equal to 0 and S squared is greater or equal to 2. Okay. So P or Q, right? Okay, so not P or Q becomes what? Not P and not Q. Okay, not P and not Q. Okay, good. Okay, so in this case, what should we do here? So why we have contrapositive here? Because we get the extra condition here. Okay, so we're going to use this extra condition here. Okay, we're going to use extra condition S greater than Z. So we know that X greater than Z. But then at the same time, we know about Z, right? So let's recall what we know about Z. Yeah, so we know that Z is greater than 0. Okay, so by transitivity, X greater than 0. Okay. And let's play some trick here. So let's play some trick so that we can use the second condition here. Okay, so Z squared here. So let's play some trick. So this trick is very common in mathematics. So maybe you want to remember this trick here. At the same time, we know that X is equals to X minus Z plus Z. Okay, so you're creating something, but then it's like adding a 0 to it, minus Z plus Z. Okay, so we want to look at X squared. Okay, so we want to look at X squared here. So what's X squared here? Then you compute, what do you get? You compute what you get. Yeah, I give you 1 minute. What do you get? Using the new expression of X, what's X squared? What is X squared? You got it? Injay got it? What do you get?
X squared
Ah,
plus 2zx minus 2x plus 1
like that.
minus z squared.
Like that? Why is there a 4 here? There's no 4 here. There's no number here. Why is there a 4? Oh, you thought it's 2, huh?
Yeah.
Okay. Okay. Sure. So this one maybe need to adjust a bit. Okay, but the point here is not to open everything. Okay, so in maths, right, you not necessarily open everything, but then you can keep it in this form: x minus z squared plus 2z times x minus z plus z squared. Just use the binomial expansion. Is it called binomial expansion? Yeah. Okay. So why is this form better? Do you know why is this form better? Okay, so if you notice that this term here is always greater than 0 because we know that x greater than z. Okay, and then this term is also greater than 0, but z we already know greater than 0. Okay, so something greater than 0 times something greater than 0 is still greater than 0, closure of positivity. So in that case here, this is greater or equals to z. Okay, but then we know about z squared, right? What's the condition we know about z squared? Is greater or equals to 2. Okay. Does it make sense? Okay. So in this case here, in particular, if you just take 2, 2 squared equals 4 greater than 2. So actually we found an upper bound for x. So we prove that x is actually bounded. Okay. Okay. Any questions so far? Okay, so we have a bounded above set and then bounded above not empty. So by completeness axiom, this sup of this x exists. Okay, so the supremum, the least upper bound of the set exists. Okay. So then what's the next step, man? So what's the next step? Next step. So the next step is we need to show that actually this upper bound is square root 2. So meaning it satisfies this condition here. Okay. Yeah. So the next part is to show this. But showing this is a bit technical. A bit technical. Okay. So to show this, we're going to show that this number here cannot be less than or cannot be greater to 2. So by trichotomy law, it has to be equal. It's a bit technical. Should we keep that? It's a bit technical. Are you interested? I ask you. I scared you fall asleep when I tell the proof. Oh, trichotomy law, right? So two numbers, right? If you compare two numbers, so either is equal, either is less than, or either is greater. So to show equal, I will show that it's not greater or less than. Oh, how do you compare sub x squared with 2? Is that what you mean? Yeah. Okay, I give you some idea first. Okay, so maybe I won't tell you the everything yet. I'll tell you some idea. So for example, suppose that sub x squared is less than 2. Then from here, you can see what's their distance between them. Because like 2 is greater than sub x squared, meaning their difference is greater than 0. Okay, if you take 2 minus sub x squared, okay, from here and then you can continue. Okay, so the continue is, so maybe the claim I put here is, so if this happens, okay, let's say, okay, let me draw a picture here. So number line is very important in this class, so every time. So maybe sub f squared is somewhere here. Right? Okay, so that's epsilon here. So the claim is for any number y, which is close enough to sub x. Okay. we will have y squared less than 2, or more precisely, let me finish the word first and then I'll draw the picture for you. So there exists a delta greater than 0 such that if y minus sub x is less than delta, then this implies that y squared less than 2. Okay, so what does this mean here? So it means that if you look at your sub x, okay, and then there's a y. So let me draw this delta first. So sub x plus delta and then sub x minus delta. Okay, so if your y is around somewhere here, this will implies that your y square is strictly less than 2. Okay.
For any number y which is positive, so that's then y squared.
And then this, how does this give contradiction? How does this give contradiction? Can you think of this statement, how to give contradiction? What does this say? If you have a sub x, okay, this is the least upper bound. And then I said that if there's a number y in between the range of this delta, you will get y squared less than 2. Y squared less than 2 means what? Means this y live in where? Live in x. Correct or not? Still remember the condition of x? You have to remember these two conditions. Okay, it's living in x. Any contradiction you can get here. This guy is the least upper bound. This guy is the upper bound. But then I say that there's a y, if it's delta near to it, then this y have to live in x. If my y live here, can or not? This y is in x. Can or not? If I have an element in x that's greater than sub x, can or not? Cannot, right? This is the contradiction. Okay, does it make sense? Okay, here is okay, here doesn't matter. But then here is matter. Because you have something that's in x that's greater than sub x, right? Okay, so this left-right controlling here is very important. Okay, if it is just one side, then don't care. But then if it's on this side, then something wrong with you already. Something wrong with your sub x. It's not an upper bound anymore. You found something in x that's greater than your sub x. Okay, you get the idea? Yeah. Okay, so the detail is in the lecture notes. You can try and see. Okay, so similarly, you can suppose the other way around. What if 2 is greater than sub x squared? Okay, you can suppose the other way around. And then get contradiction again. Okay? Okay, yeah. So detail is in the lecture notes. So try and see yourself. Okay, good. Any questions so far? No? Okay, good. So next, I'm going to introduce you the third equivalent definition of a soup. Okay? Yeah. But before that, let me show you this proposition. Again, let A be a non-empty subset. So let me write in this way. Non-empty subset A in R, which is bounded above. Then, for any epsilon greater than 0, there should be a number A in A such that A is greater than sub A. Okay, so let's draw this picture. Again, let's draw a picture. So whenever you see inequality, right, try draw some picture here. Okay, so let's see where it goes. So if you put an A here, okay, where should you put your sub A here? To the left or to the right? To the left or right? Left or right? Left, your left. Left here. Is it left, right? Sub A. A is something in A. Sub A is the upper bound. So it should be on the, yeah. Sub A is the upper bound, least upper bound. Should be on the right. Okay. And then where should the sub A minus epsilon be? So epsilon is positive, right? Okay, so if you take away epsilon, is somewhere negative, somewhere on the right, sorry, on the left, right? Like this. Okay, and then this A should be greater than this number. So imagine, can you imagine? Now I think of this epsilon as a parameter. Okay? Parameter. So usually in this class, only small epsilon matters. Big epsilon we don't really care. Okay, so you want to consider epsilon as small as possible. For example, 0.1, 0.001, 0.00001. Okay, as small as possible. So what does this statement say is, if you take any epsilon, okay, so you can reduce this epsilon as small as possible, right? So, okay, let me draw this distance again. This is epsilon, okay? So if your epsilon is getting small, you can always find an element in A living inside it. Does it make sense? Okay. Let's say, you found an epsilon, okay? But then there's no A anymore. There's no A anymore. Can sub A be sub again? You understand what I said? Let's say there's an epsilon naught, epsilon 0, such that there's no A anymore. You cannot find any element in A. There's greater than sub A minus epsilon. Can sub A be a supremum? No, right? Your place, then sub A minus epsilon will become the new least upper bound. I mean, possible least upper bound. You get what I said? Maybe 拼接 and repeat what I said. You repeat first.
So like, if there's no sub A, then if there's no A, then the sub A will not be the upper bound.
Okay, missing one condition. So can anyone add in condition to what he said? Add in? No? Okay. So first thing I want you to learn in this class is repeat what people say. Because you see, he is repeating something wrong, right? I'm not blaming you, but then we need to add in the right conditions first. Okay. Who know what condition he's missing there? So can you repeat your thing again? If you're missing A, right, then sub A cannot be least upper bound anymore. I said there's a missing condition. So what's the condition missing? Before missing A, there's something happened. Sorry? No. So before that A is missing, there's something happened. Very important thing. No, it's not about A anymore. A is correct. A is missing. But when is A missing? I'm saying, let's say if there is an epsilon. If there is an epsilon when A is missing. Okay, so maybe I can put a notation here to remind you. So maybe I can say that this A is dependent on epsilon. Okay, so I give you an epsilon, you can find an A. So this A should be depending on epsilon. Okay, so let's say I have an epsilon. Let's say E is epsilon naught. So maybe I put a remark here. If there is a epsilon naught greater than 0, such that there doesn't exist an epsilon naught in A, then my claim is sub A is not a least upper bound. This is my claim. Okay, so you're missing this thing here. This is very important. Okay, so why?
Why? So think about how to negate sub A, how to negate lowest upper bound. So to say something is not lowest upper bound, what do you need to say? Either it is not the least one, either it is not an upper bound. These two things only you can do. Okay. So one thing you can verify. Say why?
So like because there's an epsilon, there's an error in
Okay. So there's no A here, right? Meaning what? Meaning A is on the left side of sub A minus epsilon. So sub A minus epsilon should be another upper bound. You understand? Okay. Okay, so I think I'm missing something here. I'm missing something here. I should say this. I'm missing something. I said there's no A epsilon. When I say no A epsilon not here, this is such that A epsilon not greater than sub minus epsilon. Okay. So the negation of this is what? All the A should be less than or equal to sub A minus epsilon. Yeah. In that case, meaning what? Sub A minus epsilon is the upper bound. Is one of the upper bound. Okay. Because for all A in A, it is the case that A will be less or equal to sub A minus epsilon, which means sub A minus epsilon is a upper bound for A, but sub A minus epsilon is strictly less than sub A. Okay, so sub A is not the least one. Okay, does it make sense? I found a smaller upper bound. Okay. Does it make sense? Any question? No? Okay. 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 Okay, so if it is the upper bound, then this thing will satisfy. Okay, this thing will satisfy. I have a proof in my notes. It's very easy. It's just a contradiction. Okay, but the idea is this. Okay, the idea is this. The idea is this. Hey, how many of you read my lecture notes actually? How many of you read my lecture notes? Can I see? After or before anything? Got one, got two. Okay, 2, 3, 4. Xiang start reading already. I thought last time you didn't read. Okay, very good. Okay, thank you. Very good. Very good. Very good. Very good. Very good. Very good. Okay, because some students they just don't care you.
所以他才会觉得你翻译的很sensitive。就是他先遇到你的文章，然后上次有人才会翻译的那个 sensitive。
没有他是没有读，他不知道我们做，上次还没有读到做。OK，他这里 OK，It's OK，It's OK。呀，什么？应该有？没有哈 ？OK， 好。Okay, so this is one direction. So this is if sub A is this upper bound, then this will satisfy. But then you also can prove that if you have this condition, you can prove the two condition in this upper bound. Right? You can prove the two condition in this upper bound. So that actually this here, you can try and prove that this is a. So maybe I use this color. So if you have a number sub A that satisfies this condition here, this is equivalent to say that sub A is a least upper bound. Okay. Are you confusing? If I say sub A is least upper bound, are you confusing? So if I just think of this sub A is one number, Okay, if it satisfies this condition, it will be a least upper bound. It's a real solution. Yeah. So this is we can prove. Okay, we can. Okay, maybe let me write down. Let me write down. So okay, so let me write this. Let me write my claim. Okay. So let's go back to this statement here. So definition, right? So this is the two equivalent one. So I'm gonna introduce the third equivalent one. That is for every x in S. Sorry, no, not like this. So for every epsilon greater than 0, there is x in X such that S is greater than M minus epsilon, like that. Okay. So you should be able to show they are. Okay. So there are three things you can use. Okay, for your least upper bound supreme. Yeah. So just now we established from top to bottom, right? So one thing left to do is from bottom to top. So if you assume this epsilon statement, you will prove the other two statements. Okay, either one of them will work. Either one of them will work. Okay. You want to try yourself, or you want me to show you? Do you want me to show you, or you want to try yourself? Huh? From this one to the other two. You want to try yourself, or do you want me to show you? Want to try yourself, or you want me to show you? Look, quick. Maybe I ask the one beside Qi. What's your name again? Yeah. What's your name? Jingyi. Hongjun. Hongjun. Oh, okay. Hongjun. Yeah, Hongjun. Okay, Hongjun. Yeah. You want to try yourself, or should we do together? You can try yourself first. Okay. So let you try first. So if you don't understand, maybe you can raise again next class. Okay, then we can discuss. So if you assume this epsilon statement, can I prove the rest or not? Can I prove this? M less than M prime less than M. Show that M prime is not upper bound. Okay, using this step. To show that something is not an upper bound, again, what do you need to do? What do you need to do to show something is not an upper bound? Need O me? Need more O me? You contradict, you negate the statement need O. So many. Yeah, as long as there's one is enough already. Okay, not need everyone. It can't be the case also. Most of the time, it can't be the case. But it's very important. Okay, check for all and check for some is different thing. It's very hard if you don't check for all. Okay, yeah. Sometimes it's just not true for all that exists is enough. Okay, as long as you can find something that's greater than M prime, then you are good. And then the hint here is this will give you something. The hint is this statement, epsilon statement here will give you something that you should need. Okay, yeah. Okay, good, very good. Okay, let's quickly finish up two things and then we can have a break. Maybe three, very quick, real quick. Okay.
So next is a very important theorem in this course. Is called the Archimedean property. The statement is very easy actually. Okay, the statement is very easy. So for any real number, there should exist a natural number n such that x is less than n. Is this easier? I give you 0.1. What's the natural number greater than 0.1? 2, 1 also can. If I give you 100, what's the natural number greater than 100? 1000 also can. 101 also works already, ma. Plus 1. Last time I think you tell me this trick, right? Plus 1 to natural number. So this is very simple, but then how to prove it? Okay. For any number, I think you can figure out. But then, like in general, how do you give me things? In general, how do you give me the number? Okay. You need to remember the technicality here. Last time was natural number compared with natural number. But then here is real number. You cannot just say plus 1. Like 0, 1, 0, like 0.1 plus is not a natural number. So how do you fill in the gap? Okay. One way you can fill in the gap, the other way is we use contradiction. I don't care how it looks like. Okay, so let's see how I bypass the presentation of real numbers. So let's say suppose on the contrary, so I'm going to use contradiction. It's a y in R such that for every n, y greater than or equal to n. Okay, so let's suppose the negation of this. Is it negation? For all becomes the exit, right? The exit becomes for all and then just one I solve. Okay. Suppose the otherwise is true. So what does this mean? There is a y that's true for all n such that this inequality is true. Can recognize this. Can recognize this sentence here. There's something that's great. Can recognize this segment. This says y is what? N. Is an what? Upper bound, right? So there is an upper bound for what? What is that set? Natural number, eh? Is it crazy? There's an upper. Okay. So then by completeness axiom, there is a good, there is a least upper bound. Non-empty, I think you okay, right? Non-empty. Least upper x from the set. So what's the set here? Y in R such that y is greater than n for n. Okay, so this set is non-empty because I assume that this is such one of the one. Okay, so in particular, for every n in n, n plus 1 should be in n, so that this upper bound here is greater or equal to n plus 1 as well. But then what does this say? Rearranging this. X minus 1 is greater or equal to n for all n. Okay, but then what does it say? We found another upper bound. But then this upper bound is x minus 1. Previously, we said that x is a least upper bound. So there is a contradiction. Okay, so contradict that. Contradict the fact that S is the least upper bound.
Okay, so we produce a contradiction to least upper bound. So what's the corollary here? So the corollary here is n is not bounded above. Okay, so very easy proof here, following from the Archimedean property is, suppose n is bounded above, okay, by some number x, and then by Archimedean property you can find another n greater than it. So contradiction. Okay. So Archimedean property, yeah, here a real number, you can find a natural number that's greater than it. Okay, so you controlling real number using natural number. Okay, so let me draw the number line for you. So if you have some real number, then definitely you can find a natural number that's greater than it. If you have some real number, there's a natural number greater than it. Okay, so maybe this is n1, this is n2. Okay, good. Let me see. One more. Okay, one more, we'll take a break. So let me see. Yeah, two more maybe. Okay. So another corollary, very easy corollary is for every epsilon greater than 0, there should be a natural number such that 1 over n is less than epsilon. Okay, maybe it's worth to think about this. Okay, how this works from what we know just now. And then this will be using in the proof later for your function proof. You should a natural number such that 1 over is less than epsilon. Can you try and think how we work this out using what we know just now? Based on what we know. Now, this n is like going to the bottom, right? Just now the n is on the right hand side. Right or not? All right. You compare to what we know just now. The n, right? The n is on the right hand side just now, right? But then this n go to the left hand side and then go to the bottom. How? Any idea? Maybe you can play around with that inequality. You can play around with that inequality. How to apply this? Because this is true for all x, right? Okay, so if you can produce some x, then it works. So what's the x you can produce to use that theorem? So maybe I copy this Archimedean property so that you can compare. Copy. Okay, so can you try and use this theorem to figure out how to find this n? To find this n, right, you need to use this n. Yeah. Okay, so by Archimedean property that exists n in n such that 1 over epsilon is less than n. And then this what implies that 1 over n is less than epsilon. Okay. Stop the position means what? I think we do it in the real number axiom, right? We invert epsilon, right? And then I multiply with n. I invert 1 over n. I multiply n on both sides, I multiply 1 over epsilon. Okay. And then 1 over epsilon makes sense here exactly this. Because it's not 0. Okay, so I'm using 1 epsilon is in R. Okay. So that maybe in here, not that. Over epsilon is in. Okay. Yeah. Any questions so far? No? Okay, because this is an analysis-based class, you know that to prove a statement for all, what do you really need to do? How do you start? Actually, at this proof, you need to start by taking epsilon greater than 0. So you need to fix one epsilon first. And then you need to add saying that since epsilon greater than 0 is arbitrary, then this statement is true. For all statement is true. Okay. So what am I trying to say here is, if you learn in the discrete math, right? Did you remember that when you want to prove a statement about universal quantifier, you need to do something called is it called universal identification? What do you call that? Okay, I can't remember the term. Let me check. So, universal. Oh, it's called a universal instant. What's the word? Instantiation. Okay, let me find the word. This word. Okay, universal instantiation. Okay, so you move from a general statement to a specific instance first. So you want to prove for all. So you start one of them. Prove it is true for any one of them. And then if it's true for any one of them, then it's true for all. A bit twisty, huh? So if you want to prove a statement for all, you need to check for any arbitrary one, specific one. But it is arbitrary. If it's true for a specific one that's arbitrary, then it's true for all. Okay, you to do universal instantiation. And then existential instantiation is easier. So that's what I want to tell Pinky now. Existential instantiation is you just need to prove for some. But this one need to prove for all. Okay. You might think that you also only take one epsilon here, seems very easy. But then no, this epsilon, no, I don't have any condition on it other than the question condition. But the existence one, you can put any condition. As long as it works, that's fine. Okay. Any extra condition, that's what I mean. Okay. Any extra condition, it works, then okay. That's existential instantiation. But universal instantiation, you need to only take condition in the question. You cannot put extra condition. You cannot say, I want my epsilon greater than 2 as well. No, doesn't work. No? Because how about the number in between 0 and 2? No need to check. Here say doesn't matter. Okay, so can you differentiate these two things? Okay, yeah. So the real proof you need to write like this. But then if you already go advanced, you learn better already, then we will accept this blue proof here. But if you really want to write everything properly, like Qiang, like very pedantic, right? Okay, you can write in this one. Okay, do the it's true for everyone, then it's true for. Okay, so this is the full proof one. But then if you write the blue proof, it's fine. Okay. Any questions so far? Any question? Okay, maybe we leave the last one to the next part. Any questions so far? No? Okay, if no question, maybe we can take a break. Can you see if you can start signing in online or not? Maybe I'll take manual attendance as well. But then you can start try. I'm not sure whether I need to sign in or not. Let me try. Let's break until 10:15. Yeah. Can. Can you sign in? Do I need to start? I'm starting now. Okay, I start. You can try and sign in online. We'll take the offline as well. Cheng Wei, Yu Shen, okay. Ellen got, I think I called Hong Jing as well. Yu Sun, Yong Sun, okay. 石慧，修石慧，石慧有上。好，OK，他是石慧。天乐、祁阳、品杰、刘昌 Sick、浩然 here， 浩然，陈玉、李成玉，李成玉 ，OK。董百涵，王华月 ，OK。新阳，哎，新阳 are you in group one 啊？怎么好像我的 list 你是 group one 的？你的 AC 是 group two 啊？你看一下，你看一下，因为我的 AC 好像你是 group one。嗯，对，你跟什么老师说？Pauline，他说他会帮你改，为什么呢？因为你有课啊。我知道为什么你需要调我的意思是，因为你有课还是什么？哦，也没有，你想迟一点啊？哦，OK OK，他说他帮你调，他会帮你调吗？他承诺你调啊？对，他应该不会帮你做。哎呀，所以你是不能来 group 吗？还是什么？啊，你可以啊，OK OK，因为问题是现在是电子 sign in，所以如果你过了那个时间段，你就 sign 不了。哎呀，OK 好，你会 group 啊，好。风杰，一兴，一兴 OK，昌一，昌一 OK，文伟，文伟 OK，基清，昌基清 OK，俊伟，俊伟，慧杰，慧杰，安慧杰 OK，凯泽。嗯，春贤，OK，于兴here 嘛，其实是于兴啊，于兴长这样，我忘记了，有没有在？哦，于兴是那个每次跟你坐一起的啊，OK 好，你知道他在哪里？不是，哦，钢琴好，俊汉，OK，俊汉，恒玉，张恒玉，OK 好，maybe I can show you something while waiting resting. There's one very interesting video and very similar to my philosophy to Max. This guy, he's a Tsinghua PhD. It's also one of my favorite Max channel. Yeah, wait, let me see. Yeah, this guy. But the title is very interesting also. Wait, it's just released yesterday. You guys know this guy? Maybe I show you some part of the excerpt.
年、18年都在为了高考努力，这是我一模考得非常好。
Maybe Chinese people will get more related.
贴了一个支持后
He's
劲，
speaking about golf.
然后把我扣分的卷子都放在上面。然后呢，在2016年我如愿考上了清华大学，然后而且进入了摇班，这是我当时意气风发的样子。那个时候我还很瘦。现在呢，我是一名人工智能的博士生，但是我更受人熟知的一个身份是一个自媒体博主。这个啊，我做的这个账号呢叫做慢视沉思录。我想先调查一下啊，在座的各位之前有刷过我视频的举个手，我看一下。哎，有，这里也有，这里也有，不错不错不错。不过其实我做博主这件事情，我自己的家人还有老师其实都不是很理解。大家很容易就觉得，哎，你是个学生就应该好好学习，你是个研究生就应该好好做科研，对吧？你为什么去做起了一个自媒体的科普的博主？这就是我今天想跟大家分享我的故事。那就是在我看来，很多人都对这个东西有很大的误解。数学，在我看来，这是这个世界上最美妙的一个学科之一。但是我知道，对于很多人来说，数学这 MATH 的全称啊，应该叫 Mental Abuse to Humans， 人类精神虐待，对吧？觉得好好的人类为什么要学数学呢？因为大家想想看，我们从小到大接触的数学都是什么样子？先练这个加法，我刚才这个人说好简单，那很快呢，你们就会接触到小数的加法。也很简单，再往后就会接触到分数的加法，啊，再往后就会接触到指数与最数的运算啊，然后接下来你们还会算各种各样的根式的化简，这是解方程，然后解方程组，然后算数列，算三角函数，算解析几何，算立体几何三角数。你们有没有发现啊？这都是你们以后一定会面对的，各位。你会发现，数学很多时候我们数学一直就在讲两个计算，来来回回的算，反反复复的算，同样的一个乘法，对吧？有那么多种乘法，就让你换汤不换药的去算，所以很多人学数学就会学得非常的痛苦。但是不像告诉大家，数学是这样，很多人一辈子都不想再看数学。但是我作为一个有幸见过真正数学的人，我想让大家知道真正的数学它可能长得是什么样子。开始讲这个，我来先给大家看这样一个问题。想象一下
Okay, I jump this question and then jump to the part you talk about integral.
数字相乘，把这个方程将就是这样，你的离散后进去的那一次，对吧？看看会发现后中。或者说我套路19，然后有些机构就由此赚钱。都在很多时候，数学写作，比如说这个人在研究这个问题，但是他在我的老家这样一个3、4线的小城，在那些人口和高考的大省，这些学生每天都在埋头经历着什么样的事情？比如说，这是我一次初中考试，初中考试当时是要算这个地方英语的面积，这个面积啊。我们平时算的时候都很简单，因为它看起来就像个平行四边形，于是需要把长乘宽、底乘高算出来，就这个值，非常简单。但是那次考试，这个老师把染色点错了，他点了啥呢？他直接点了整个空白区域，然后再次考试的时候，这个阴影区域变成了这样。在座的学生可能会觉得啊，这不就是多了一块吗？但是学过大学的家长应该知道。这意味着你要算这个东西的面积，这个东西的面积叫做微积分，就是应该是要到大一才会学的东西。然后我们就出在考试题上面，然后我当时所有同学都懵了，但是我很开心，我说这次老师终于考出了一点课本上没有的东西了。然后我就在考场上呢，我就自己去做，我把它分成 n 份，这个你现在不需要看懂，但大概知道我当年有这个流就可以了。然后。我就在考场上硬去算，我去算这个求和，然后在 n 很大的时候，我算出来了这个面积是2/3，然后所以2块就是4/3，再加上原来的就是10，4加10，34，我非常得意的把这个答案交了上去。 最后呢，老师给了我一个差。老师说，所有人一眼就知道这个题目出错了，就你还那么认认真真算这个玩意儿的面积，这是闲的蛋。他给了我一句话，答案就是10，就你错。这个高考不考，大家之后这样的话会听到很多，比如说不要看这个，不是浪费时间。比如说有空多看自己错题吧，你现在成绩还差得远。你的这种探索，哪怕是我在考场下午的20分钟自己创造了微分，老师也只会给你一个差。这种感觉什么？这种感觉我后来才知道有一个心理学的史，叫做跳蚤效应，就是科学家把一堆跳蚤放在一个罐子，跳蚤扔了很多跳蚤，它会跳到这个罐子的外面，然后呢，科学家就拿盖子把这个罐子上面封住了，然后跳蚤跳到上面就会挡住，就会头疼。就这样关了整整3天，把盖子打开，这些跳蚤明明是可以跳出这个罐子的，但从此跳蚤再也不会跳到高于这个罐子的高度。你有没有想过，这个罐子的盖子就是高考考纲，这是考试的要求，这里头的跳蚤就是我，而我想要去想出一些在考纲之外的内容，就头就重重的撞上了这个罐子。等大家高考结束，进入大学，这个罐子上面的盖子打开，但很多学生依然不会跳到比这个罐子更高了。哪怕在清华和北大，我也见过很多很多的同学，他们走上科研之后，依然在以做题的思维去处理，他们依然不自信，也从来没有想过哪一天我可以想到一个全新的课本上都没有的东西，去探索我自己可能的知识，发现全新的东西。很多人抱怨说中国的科研亦步亦趋，其实早在中小学就早有预兆。这件事情在我的那种老家3、4线的小城，在山河4省，在那些人口特别稠密、考试压力特别大的地方更加严重。
Yeah, okay. If you're interested, you can continue and watch your stuff. Okay, so, yeah, so this is what I wanted to do in my class. I'm not trying to cap you in way of bottle or what. So I hope you can jump out from your maybe comfort zone, try and explore things. And before you really go into society, okay, to prepare yourself to go into society, to face challenges. Does it make sense? Yeah. Okay. So there's a class he mentioned, right? Yao Ban. That Yao actually is the Yao Xing Tong, is the Qiu Chen Tong. Okay. The Chinese mathematician professor. Actually, he's from Hong Kong, and then he went and become Harvard head of department of mathematics, and then now he's kind of retiring. He went back to Tsinghua, and then he opened now sort of a maths center in Tsinghua. Yeah, so they recruit young students even before they finish Gaokao, I think, to the class, and then they train them, okay, to be mathematician. Okay, so he can comment on Tsinghua. I'm not from Tsinghua. I cannot. Okay, yeah. So this is what happens. Okay, so if we really want to do good research or what, we have to jump out of the mindset of doing question only. Okay, we need to think about what this question is trying to ask me. Okay, then you can solve literally any question actually. Okay. All right. So before we go to the next section, we have to talk about the density of rational and irrational, and then this will kind of fill up the picture of real numbers. Okay, before we jump into the next part. So what's the density of rational and irrational here? So the statement is in between every distinct real number. Let me put this shorthand notation. There exists a rational number and an irrational number. Okay, so what's this picture here? Let's say irrational, I call it
I don't want to call it I. I is complex, right? Let's call it L maybe. Okay, so the picture is looking like this. So give you any y here, you can find a real number or a irrational number.
Okay. So if you can imagine, I can plug this theorem to this I and L. Right? I and L is real again. I can find
Real and irrational again. In fact, any two of them I can find rational and irrational again. Okay, so that's why
we have a picture of this line here. Because you can imagine I fill up all the dots on this line. Can you imagine? Okay, any two real number I can put real number and irrational. Any two I can put real number. So that's why I can fill up
this dots on the line. I can fill out the line. Does it make sense? Okay, any two of them I can find.
And then any real number I can find a real number greater than it. So I can extend it. Does that make sense? Okay. Okay, I can extend it and then I can fill in the dot. So that's why I got this line. Imagine. So far, like here is week 3 already, right? So first week I tell you P and R maximum, right? +1 +1 +1 +1 +1 +1. And then now I tell you between these 2 + 1, there's rational, irrational. Then you can fill everything. It become a line.
Okay, so how to prove this? So this proof is not too hard. Okay. Very easy one. So proof, since x is not equal to y, without loss of generality, we will assume that x less than y. Okay.
You guys know what is without loss of generality? Yeah. So can you explain?
For example, you have
Mm.
the ball.
Mm-hmm.
In this case, and then something for the also
Okay.
or
Yes, right. Okay, so in general, right, you need to cover all the cases. But then without law of generality, we'll say that, let's say I prove for these cases, the other proof will be working similarly. Yeah. So you prove all cases as well. Okay. Without loss of generality. So meaning this assumption here doesn't change the fact that how you prove the other one. Well, this assumption, how should I put it? This assumption doesn't affect the truth of the other statement, and also the other statement should be proven similarly using similar proof. Yeah. Okay.
Okay. Good. So we assume x less than y. So by corollary above, or by above corollary, there exists n in n such that 1 over n is less than y minus x. So this is the epsilon.
Okay, because y greater than x.
Okay, so this epsilon is greater than 0. Right. Then, so first thing is I want to produce a rational number in between 1 and x. What do you think? Can you imagine anything or not? So let me put a x here, put a y here. So this distance here should be greater than 1 over n. Okay. So can I find a
rational number first in between here? Is it possible?
maybe to help you think about this? Let's say, how about there's a 0 inside here. Okay, there's a 0 inside here.
This is less than 1 over n means what?
What does it mean? So let me put them closer a little bit. What does it mean here? So this one is less than. So this means that, let's say I break this ruler, let's call our number line ruler, into a 1 over n
Recording. Measurement. So you got 1 over n,
2 over n, 3 over n, like that, right? So maybe let's make this even smaller. less than 1 over n. Okay, what does this mean here? I said this one n, 3 over n, for example. Okay. Is it less than 1 over greater than 1? Oh, greater, sorry. This should be greater. Is it greater? Yeah, greater. Greater or less than? Greater, right? Okay, so meaning I need to like cover one of the cover one of the 1 over n. Okay. Okay, does it make sense? Okay, greater, not less than. I think I see something wrong just now. Okay, so if it's greater than 1 over n, see from this picture, I can find some rational number here. What are the rational number I can find here based on this picture? In between x and 1. Did you see rational number in between x and 1? Did you see? 2 over n or 3 over n also works, right? Okay. But then what's the worst case here? What's the worst case here? The worst case here could be, I can move this around, right? Let's move these two around. Maybe it's here. Then in this case here, what's in between s and y? 3 over n. But then this is the worst case. Why? You must at least find one of them. Because the gap is greater than 1 over n. Okay, the gap is greater than 1 over n. Okay, if the gap is less than 1 over n, what could happen? It could happen that you just live inside here. Okay, you cannot find some m over n here. But then it doesn't imply that you cannot find irrational, rational. It's just that it's not convenient to find. Okay, does it make sense? Okay, so let's see how do we prove this from this observation here. So then we just let m to be the smallest integer such that x is less than m over n.
Can you find this? Is it possible to find this? Smallest integer less than m over n. I think this technically have to be a lemma actually, okay. Because I only tell you that you can find a natural number that's greater than the real number, right? So for example, you can find a natural number m such that nx less than m. But then there's a negative thing.
I'll prove it in my notes. Maybe you can try and exercise. Okay. Okay, let's say we can do this. Yeah, let's say we can do this. So our claim is this is the
Right, so this is exactly the idea that we had just now. Okay, we find the smallest integer such that 3 over n is greater than x. Right, this is the smallest one. 4 is not the smallest. 5 is not the smallest.
okay, let's show this. So what do we have to do here? So what are we left to show here?
We are just left to show m over n less than y, right? Because we already found m over n greater than x. So this is the thing that we left to show.
Okay, we need to show m over n less than y. Okay. So what do you note here? Okay, so note that m minus 1 over n is less than or equal to x.
Okay, less than or equal to x because this is the smallest integer that's greater than such that m over n greater than x. So if you go down one more, if you go down by 1, then it will be less than x already. Okay.
So what does this imply? This implies that m over n actually less than or equal to x plus 1 over n. Okay, does it make sense?
I just move 1 over n across.
I add 1 over n on both sides. Then what's next? But then we know that y minus x is strictly greater than 1 over n. Okay, here is strictly greater. Does it make sense?
Okay, so 1 over y minus x is strictly greater. So I use inequality.
But then this is what? This is just y. So y is strictly greater than m over n. Does it make sense? Okay. Good. Good. Question? Go question. Any question? Okay. So maybe
the hard part is this one. This one I need to explain. Okay, so why there is a smallest integer such that x greater less than m over n.
because previously I just told you this. Yeah, I just told you this. Previously I just told you this. But then why it works for integer? But can you imagine what you need to do? Can you imagine to use this Archimedean property to show that? What do you need to do? What do you need to do? Any idea? What do you need to do? Do you know what am I asking or not? I'm at Qiang, repeat. Can you repeat what am I asking? How to prove this lemma? What did I say? If Qiang not listening, then I think the whole class GG already. Chungxian.
Yeah, how to prove this lemma? No idea. Okay, so I give you some idea. So I want to find an m such that m over n greater than n x, right? Okay. So just now I have an Archimedean property says what? For every real number x, there exists a natural number greater than x. So why not you put this n across? So nx less than some natural number. Does it make sense? Okay. So for that part, okay. But then now the problem here is it could be integer, and then you want the smallest one. You want the smallest one, you want the integer. This is two things. Okay. So if nx is positive, then that natural number given to you should be positive, obviously. Okay. And how to find the smallest one? Then you need to use the upper bound property. This upper bound property. And you use a bounded above. And is it bounded above set? Yeah, bounded above set. I mean, this set is just nx, I guess. This set is just nx. And then I think the technicality lies in negative x. The technicality lies in negative x. Because if you just treat this as a real number, the natural number could be, it's just positive. You cannot go to negative one. You understand what I say? So you need to somewhat introduce a negative sign into it so that
how should I say it? So let me draw it to you. So so let's say your x is somewhere around here, right? Archimedean property will just give you some number in here because it's natural number. It's on this side. But then you want something even smaller, maybe, perhaps. Okay. So the way to do this is my idea. You need to swap this x to the other side first. This is just my idea. I will need to write down the name. I'll prove it to you. I will add it into the note. Okay. Okay. So you see the problem here? You see the problem here?
So if you just use Archimedean property, the bound that the Archimedean property give you cannot be negative. It's natural. But then if you go to the other side of, that means you want to find something less than x, not greater than x. But then this something less than x should be a bit smaller than the one that's greater than x. Okay, I'm talking rubbish. Never mind. I'll show it to you later. Okay. Yeah. Okay. So this is about it. How about irrational? How about irrational? What do you think? How about irrational? How about irrational? Maybe left as an exercise. Maybe I'll tell you what to do and then you go back and check. So for irrational, you can let k be the smallest integer such that square root 2 plus k over n is greater than x. Okay, so meaning instead of consider a rational number, you pass irrational to here. So make this number irrational. Okay, and then check. Yes. How to prove that's irrational? Very good. How to prove that's irrational? I think need to use contradiction. Suppose is rational and then and then you should contradict that this guy is, maybe you will find out that this guy is rational and then contradict that square root 2 is irrational. Yeah. You want to try and write it out? Yeah, try and write it out and then send to me. I can include into the note. Yeah. Yeah. Use a contradiction proof. Okay, good. Any questions so far? No question. I think this is a kind of a big problem. I will try and solve this lemma here. Okay, so let's go to next part. Okay, so we settle our real numbers. So now we got the real numbers now. Okay, always bring real number to this class every time. Okay, bring the line. Okay, make sure you don't forget your line. Next part is about sequence. Sequences. You learn sequences in calculus 2, right? Yeah, okay, sequences. So kind of fresh memory. So sequences is just I pick up some number from this number real line. Okay, I pick some number from this real line and then I put into sequence. Okay, two important point here. Okay, I pick numbers and then I put it in sequence. Okay, so definition. So what's the sequence then? One way to define sequence is using a function. So a sequence of real number, so we denote at bracket an, is a function. Okay, a from natural number to real number. Okay, so a from natural number to real number. So what do I mean by that? So meaning I say, what's the number in first place? Okay, you need to tell me a1. Second place, you need to tell me what is a2. So basically n to an. Okay. So some other notation you see in textbook is something like this. You denote like bracket. Instead of a set bracket, you have curly bracket, you have a round bracket, or round bracket with telling you where I start n. N greater than equal to. Okay. Okay, does it make sense about sequence? Okay. So it's a function. It's a function from natural number to real number. Okay. What's the first place? What's the second place? Third place? What's the number? So let me give you some examples. This examples, increasing sequence, an equals to n. Can you tell me what sequence is this? Huh? 1, 1, 2, 2, 3, 3. Just 1, 2, 3, 4, 5, 6, blah, 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 blah. Huh? What? Oh, thank you, thank you. Okay. 1, 2, 3, 4, 5, 6. Okay. So in graph, what did you see here? Okay, because I say it's a function, right? So let's say here is n, here is r. Okay, so 1, 2, 3, 4, 5. So this is like a linear graph, right? Okay, increasing pretty fast. Okay, so this is one of the sequence. And then the other sequence maybe you learn about Fibonacci sequence, right? Fibonacci sequence. So how do you write down Fibonacci sequence? You should write it down recursively, right?
recursively. So for example, you should define what is the first term, and then second term, and then the subsequent term will be just the sum of the previous two terms. Okay, make sense? Okay, good. And then the other sequence maybe is promising is alternating sequence. Okay, for example, this sequence here, what does this sequence do? Alternate between 1 and -1. Okay, start with -1 or 1. Our natural numbers start with 1, right? Okay. Otherwise, I put an n0 there. Okay, so let's start from -1 and then 1 and then -1, 1, -1. Like that. Okay. Okay. All right. Okay, good. So after talking about sequence, right, the next thing we want to talk about is about the convergent. Okay, so what's convergent? Okay, so now this is the first epsilon definition you will encounter. So please pay attention. Okay, so we'll define that a sequence converges to a real number if for every epsilon greater than 0, there exists an n. Okay, n might be depending on epsilon. N in a natural number such that for all little n greater than n epsilon, this implies that the distance between an minus L should be less than epsilon. Okay.
There is a very good reason why we put this epsilon here. Sorry, put this modulus here. Because we don't care whether it approaching L from the left or right. As long as it get closer, we are good. Okay. Okay, so what's the idea here? What's the idea here? So let's give you some examples. I claim that this 1 over n sequence converges to 0. Okay, so my L is 0. This is my L. Okay, so how do I show this? Well, first thing you need to understand your sequence first. Try and plot your sequence. Okay, try and plot your sequence. So let's plot my sequence. So can you recognize that my sequence is like decreasing? So for 1 is 1 over 1, and then 1/2, and then 1/3, and then 1/4, right? And then getting smaller, 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 but never touches the x, right? Never touch. So how to prove that this is converging to 0? So let's discuss first, okay, about this epsilon delta, and then we'll try to write down the full statement. So what sort of epsilon you can try? What sort of epsilon you can try? Can I try epsilon equals to 1 first? Okay, so let's try epsilon equals to 1. Okay. Yeah, epsilon equals to 1. Okay. Epsilon equals to 1 says what? Maybe I draw a line here. So if I want to say that this converges to 0, right? So L is 0. I'm saying that for every epsilon greater than 0, there should be a capital N epsilon such that for all the small n after the n. So n, where is n? N is here. Okay, n is the x-axis. N is this x-axis here. Okay, then an minus 0, okay, should be in this epsilon strip. Should be within this epsilon strip. Okay, can you give me capital N epsilon now? N1, for example. What N1 you can take here? What's the N1 you can take? Can you tell me like you can take N1 to be what? Try. Okay, try 1. I try. Try 1. Okay. So it says that if you pick N1 to be 1, that's mean for all the n greater or equal to N1, so meaning got 1, 2, 3, 4, 5, 6, 7, n. Then an minus L need to be strictly less than epsilon. So in this case, says what? An minus 0, which is just
AN lah. Need to be strictly less than epsilon. Okay, then this is true for all little n greater than or equal to. Is it possible?
Is it possible? What is A1? A1 is 1. Is 1 less than 1?
No, right? Okay, 1 is not less than 1.
But 2 is okay or not? 1 over 2. 1 over 2 less than 1. 1 over 3 less than 1. 1 over 4 less than 1. So it doesn't work, right? So can you move your N1 a bit? Can you move your N1 a bit? Move to where? N1 doesn't work, right? So try 1 doesn't work, try 2 lah. Okay,
Correct or not? Okay, so this one have to be 2. Okay, let me write here. So this one have to be 2. Otherwise, A1, which is 1 less than 1, is absurd. Crazy. Okay. Okay. Makes sense. Okay, let me try another one. Let's try another epsilon. Maybe someone can give me some other epsilon. Yongsun, can you give me some other epsilon? Your favorite epsilon? Huh? 1. What? Can you pick another epsilon greater than 0? That's smaller than 1. Smaller than 1, bro. 1 over 2. Okay, good. Okay, let's try 1 over 2. So how about 1 over 2? Epsilon number 2. Okay. In that case, maybe can I check with Sihui? Okay, Sihui. What's the N2 you can pick here? What do you think? For what is the N2 you can pick here? 3? Okay, let's try with 3. So if we pick N2 to be 3, is it true that for all little n greater or equal to 3, absolute value of AN should be less than half? All right, let's check this.
So what are the number that's greater than 3? 3 greater or equal to 3? 3, 4, 5, 6, 7, 8, right? Okay. So for A3, what do you get?
A3, what do you get? Yes, A3 is 1 over 3, which is obviously less than half. And then similarly, if you go further down, get A4, A5, A6, it should be always less than half. Okay, so it works. Okay, yeah. Okay, makes sense so far? Makes sense? Okay, good. Let's prove this in real terms, and then we will finish the day. Okay. So let's prove this. So in general, how do we prove this? Okay. So if you can see here, I can change a lot of epsilon, right? And then I need to pick different n epsilon. So how do I do it in general? Okay, so this is how we do it. So let's prove to you how we do it in general. So first of all, I pick any epsilon greater than 0. You give me any one of them. Then we must show that. So what do we want to show? We want to show that there exists an n epsilon in n such that an minus 0, which is the absolute value of an, is less than epsilon. Okay, for all n greater or equal to n epsilon. Maybe I put here lah, so that I keep the order, so that you don't confuse. Okay, so how do we do this? How do we do this? Huh? Let n be 2 over epsilon.
N epsilon be greater than over epsilon. So take a number n epsilon such that it is greater than over epsilon.
Okay. Sure. Okay. Sure. Okay. Sure. Instead of doing that, let me do this. I think for now the 2 doesn't matter, right? Okay, let me try. Or I'm going to pick 1 over epsilon.
I try. Okay, let me try first. Okay, so by Archimedean property, okay, so what we can do is we can choose n epsilon in n such that 1 over n epsilon is less than epsilon. Okay, maybe you don't know why I have to do this, but let me show you the next thing. So, but then this sentence, everyone agree or not? This is what we had for Archimedean property, right? The corollary, corollary. Do you remember? I can find a natural number such that 1 over n less than some real number. Okay, but then what do we do here? So we're going to check for any n greater or equal to n epsilon. So what do we have? Actually, what is absolute value of 1 over n? What is the definition of 1 over n? It's just, sorry, an. It's just 1 over n, right? But then 1 over n is already positive. So it is just 1 over n. Okay. And then what's the relation between n and n epsilon? We only care about the small n that's greater or equals to n epsilon. In other words, if I invert it, this inequality will change as well. But then do you still remember how we choose this n epsilon? How do we choose this n epsilon? And choose it such that 1 over n epsilon is less than epsilon. And then all together, what do we show? I show that the absolute an is less than epsilon. Does it make sense? Okay. So maybe is everyone agree we finish here? Because this is what we want to show. Okay. So maybe in practice, you don't know how to choose this, but you have to settle this. So this is the part that determines how you find this n epsilon. Okay. So in practice, I think in you are teach by Dulic, right? Dulic, how they tell you to find epsilon delta t, they ask you to do some working first, right? Okay, so you need to make sure that this inequality true first. Okay, then you need to fix how you find your n epsilon. Does it make sense? Okay, you need to find your n epsilon such that this inequality works. Okay, so you should figure out starting from this inequality. And then this will suggest you how to find this n epsilon. And then why the existence of this n epsilon is because of the Archimedean property. Okay, why you can find this kind of n? Because of Archimedean property. You can find a natural number such that 1 over the natural number. Okay. Does it make sense? Yeah. No question? No question? No question? So did you realize that in this proof, it's different from what we had here? We are not like looking at every epsilon, find you an n epsilon. I'm just using a property to tell you that this number exists. So, you understand? I didn't tell you how to find it. I tell you this number exists only. But then this is what this definition wants. It just existence. So to find it, what's the moral story here? To find it actually very depending on what sequence you use. You understand? Very depend on what sequence you use, depend on what epsilon you want. You understand? I cannot tell you everything, but I just can tell you this thing exists. You understand? Okay, I don't have a general formula to help you figure out for every formula for every sequence how do you find this energy. Okay, but then I tell you it exists. Okay, by this Archimedean property. Okay, make sense? Okay, so this proof is like an existent proof, but without telling you the formula. I cannot find it for you, but I tell you there is one. Okay, from the general statement. Okay, then so the last definition is this. So if this epsilon definition works, and then we will define the limit. Okay, we will call it a limit. We'll call this L the limit. And then we will write this notation. Limit of an and when n will be is and or we will write an converts to L as n goes to infinity. Okay. So for now onwards, you should think about this limit sign here as the epsilon n definition. Okay, for every epsilon, you should find an n such that for all the small n greater than the big N, the distance between a and n, the limit should be less than. Okay, so how it get closer is because the epsilon should be arbitrary. You can make the epsilon as small as you like. As small as you like. As long as it's greater than 0. It's not 0. So the arc here is not 0, but then it's as small as you like. It could never equal also, but then as long as it get closer when it get far, it's fine. Is it not? Okay. Any questions so far? Any questions so far? No question? Any comment or any comment? Go back study first. Okay, good. Okay, go back study, and then if you've got question, you can post on Moodle or you ask in the next section. Okay. Can get what I said just now? Yeah, okay. Okay. I mean, like, if you got question, you can ask now. Okay. Okay. If not, bring your question next time, and then we can answer that. Okay, try and think about this limit. Very interesting stuff. Yeah. Okay, the epsilon is not 0, but can get very small. Maybe I draw a picture for you to imagine. So let's say this is L. Okay. Your sequence could be getting something like this. Very close to L, but not L. Okay. I purposely draw it up and down so that it doesn't matter you approach from top or from bottom as long as you get very close. Then we say L is a limit. Okay. Go question. Go question. You looks confused, but you don't want to ask. Okay, sure. Can. This is a very useful skill. Okay, you need to know what you confuse with. Okay, good. Okay, in that case, see you tomorrow. Okay, see you tomorrow.